Hello, welcome. So in this video, I'd like to explain how to go from a digital circuit in a simulator to actually running that circuit on an FPGA. So this is a tutorial for electronics enthusiasts. So I expect that you know something about electronics enough to build something in digital and get it working. But maybe you're new to FPGAs and you don't really know how to build code and get it working on the FPGA. So this will be explaining how to basically get that running on an FPGA. And I will be using open source tools for that. So what to expect? I'm not going to heavily edit this video. Sorry about that. I'll do a light pass and probably some automated editing that I have, but otherwise this video might be a little bit longer. You can always run it at like 2x speed on YouTube if it's not fast-paced enough for you. So hopefully that's okay. I'm also going to assume that you know digital electronics well enough to build a circuit, and that you have something built in digital that you might want to run on an FPGA. And I'm also going to assume that you have a cheap FPGA to run it on, and I'll make some suggestions in just a moment on what to purchase if you're interested. So what's covered? Well, there's some modifications that you'll need to do to a digital design in order to get it ready for the FPGA, so I'll go into that. So for example, overriding some embedded circuits with a custom Verilog implementation. Also, I will be covering using block RAM in the FPGA, and getting that to work with digital and the FPGA is a little bit tricky, so I'll go into that. I'll also cover exporting to Verilog, simulating the design with Verilator, and this is a pretty important step. Writing a make file, so I'll be using make to automate building the project, and then compiling that Verilog into a bit stream so that it can be flashed to the FPGA. So some prerequisites. You obviously need an FPGA, and my recommendation would be the Ice Sugar. It's quite inexpensive. It's pretty awesome. I don't know if you can see it in the video, but here on the PMOD ports are a bunch of resistors, meaning that it's really hard to short out the PMOD ports. And so it's just a lot more beginner friendly in that regard. And also, in order to program it, you just drag and drop. It appears as a USB thumb drive, and you just drag the bitstream files onto it, and it'll program it for you. So if you don't want to use IsisProg, which is what I'll go into, then yeah, that's the simpler way to do it. It also has an up5K, which is a slower FPGA, but the FPGA itself has 128 kilobytes of RAM on it, which if you don't need to go off of the FPGA, that's going to be a lot easier. As soon as you start interfacing with external memory of some sort, then we're talking an order of magnitude more difficult. And if you're just starting out, go with easy. So this design will run my CPU at 20 megahertz and my VDP at 50 megahertz, which is quite slow for an FPGA. There's much faster FPGAs out there, but like I said, it has onboard memory, and that counts for a lot. So I would strongly recommend this one. Another option, if you don't want to order something from China, is the Icebreaker. The Icebreaker has basically the same chips on it. The interfacing is a little bit different, but not that much different. It also has the same thing where the PMOD ports have resistors on them, so you're less likely to short them out. And it comes with this extra PMOD attached to it, which is kind of nice. It's only slightly more expensive than the previous one, and you can buy it from either 1Bit Squared, and they have shops in the US as well as the EU. You can also buy it from Crowd Supply, and you can buy it from Mouser, which is quite nice. So this is another option if they have stock. I know the Ice Sugar is currently in stock. I don't know about the Icebreaker. So either one will work, and there's very little difference between them. They both use the exact same FPGA, so both are good options, depending on what's easier for you to buy where you live. Now, required tools, and I should probably put this on here, but Linux, I don't know Windows, and I know a good chunk of you are on Windows. You can install the Windows subsystem for Linux, and that would be my recommendation because Make is kind of designed for Linux type operating systems. So if you don't have a Mac or a Linux machine, then following these instructions will be a little bit difficult. It's still doable. I've seen that there's versions of Make for Windows. And if you can get Verilator to work on Windows, then by all means, you can stay with Windows. But you'll need to do some adaptation of some of the code that I show later in the tutorial. So there's two ways to install the open source FPGA toolchain. The easiest way by far is Appio, and you can get Appio here. There'll be a link also in the description of the video. And the other option for you is to compile from source. And there's instructions on this website here. And again, link in the description. This is the one that I did. So I won't be showing how to do Appio, but Appio makes things a lot easier. So if you're going with Appio, here's some of the commands that you'll need to run. The Appio drivers is only if you have the icebreaker, and the Appio install GTKWave is also only if you're on Windows. Otherwise, if you're on Linux, you would use your package manager to install GTKWave. You'll also need the Linux subsystem for Windows. And these are also some programs that you'll need. You'll only need IceSprog if you have the iSugar. Any other FPGA, you won't need IceSprog. And then you'll need Yosis, the ICE40 toolchain, and Verilator. If you want to install from source, there is also this post here that has some good instructions. I'm not sure why I had two different links for the same thing, but there you go. All right, so what are all of these tools that I'm talking about? What do they do? Well, Make automates building and compiling, usually of software, but in this case, we'll be doing gateware, I guess it's called. I'm using Make because it's much simpler than other systems. There is something called FuseSock, and I've been evaluating that, but I don't feel comfortable doing a tutorial on it because it's much more complex. There's a lot more things to learn. I could do a whole video just on FuseSock, so I can't recommend that at this time. It's not really beginner friendly. Whereas Make, I feel like there's very little extra syntax you need to learn. It's really straightforward. And it's also very old and extremely well documented. There's like probably thousands of websites out there that document how to do stuff with Make. So like really it's straightforward. And the vast majority of it, you just copy and paste from some website somewhere that tells you how to do it, which is exactly what I'm going to do in this tutorial. So don't be intimidated by Make. It's really easy to use. Now, the next one you'll need is a program called Yosis. And Yosis is a synthesis or synthesizer. It takes Verilog code and converts it into a bunch of components and wires. So think of it like a translator, but it also does some optimization and simplification of the circuit so that there's less hardware that needs to go onto the FPGA itself. And it also knows about what hardware is available on the FPGA, and it can map them, but it only does the first pass and the next software does the rest. So it emits a JSON description for the next step. Then you have NextPNR. NextPNR is a place and route software. So just like you would place components on a circuit board and route them, here you need to plan out where each component is going to go and then figure out how to wire up all of those components. And an FPGA is basically just an array of simple hardware components. They're called LUTs or lookup tables, connected together by a fabric of wires. And those wires are configurable so that you can route a signal to any other place on the FPGA. So if you want to know a little bit more about how the FPGA works, there's other videos out there. I can link a fairly good set of tutorials by NANDland in the description, and it'll kind of introduce you to some of the concepts that you would need on what an FPGA is and the beginnings of doing Verilog. So that's basically what this does, and it also takes a description of what external connections are assigned to which pins on the FPGA. And the third thing that it does is verifies that all of the circuits are going to meet the timing constraints, since that's pretty important. You want to make sure that all of the setup and hold times are being respected, and it'll also check the propagation delay and make sure that your clock speed makes sense. So the nice thing about an XPNR is it'll tell you what your maximum clock speed will be, which is very useful. And then it's not the last step in the process, so it emits a description for the next step in the process. And the next step is IcePack. And IcePack just converts the output from next PNR into a bit stream. So it just produces a binary file. And then the last step is to actually flash it onto your FPGA. And for the Ice Sugar, this is just dragging the bit file onto the FPGA's drive. But you can also use Ice's prog, or for the Icebreaker, you can use iceprog. Another program that we'll be using is Verilator. And Verilator basically compiles Verilog into C++, which can then be compiled into a binary and run. So this allows for very fast simulation of Verilog designs. It's much slower than an FPGA, but there are cases where you really do want to run it in simulation first. As far as I know, this is the fastest open source simulator out there. It's quite a lot faster than Icarus Verilog. So it's very useful. And what I generally do is I get it working in Verilator first, because Verilator will find a bunch of problems, and an FPGA is just basically a black box, or a black chip, I guess. You can't look inside it. You can't see what the circuits are doing. So Verilator allows you to generate debug traces. And we'll look at these in a moment when we get into setting up Verilator. But essentially, it gives you a way of examining exactly what every single wire in the entire design is doing. And it does it very quickly. So then that can help you visualize a timing problem, because digital doesn't always catch timing problems, whereas Verilator almost always does. It's been very rare that I've got it working in Verilator and it didn't work on the FPGA. And of course, these debugging traces really, really help for that. It also has a very helpful linter, so it'll catch a whole bunch of common issues, much more than Yosis will. So we'll be setting this up as a linter as well. So what do we need to do? Well, the first thing we need to do is go through this flow where we go into digital and we mark any circuits that we can't export that we'll need a Verilog version of. And I'll go into what kinds of circuits those might be in just a moment. Then we export that to Verilog, and we also need to write a little bit of Verilog, and this will be mostly copy and paste, so don't be intimidated if you don't know Verilog very well. I don't know Verilog very well. I know just enough to be dangerous, and that's it. So don't be scared off by this. It's mostly just copying some Verilog code to make certain things that you can't do in digital possible. The other thing that we'll need to do is configure the PLL. So most FPGA boards have a fixed oscillator on them, so the clock rate can only go at a certain frequency. And quite often that's just not flexible enough. You want to have a clock that runs at a completely different frequency according to the design. So a PLL is a phase lock loop. And what it does is essentially converts one frequency of oscillator into an arbitrary frequency. And there's certain limits on this, but yeah, a PLL is what you need in order to convert the, I guess you could say, hardwired oscillator frequency into whatever arbitrary frequency you need for your design, and you'll almost always need to use the PLL for something. So once you have the Verilog set up, then you need to set up a makefile with these steps. The first step is to synthesize it with Yosys. Then you'll get a JSON file. Then you need to place and route it with NextPNR, and you'll get an ASC file. And then you pack it into a bitstream with IcePack, and you get a bin file, and then you upload it to your FPGA. So let's dive right in. This is the design that we'll be working with today. And this is basically a UART with 2 FIFOs on it and a state machine. I've also blocked out the PLL up here so that we can replace this with a Verilog module later. So let's get into a bit of a demonstration. In the UART here is a telnet module. So this is a key difference between digital and what we'll be doing in the FPGA. In digital, there's not really a way to do a serial UART, but there is a telnet module that will allow you to communicate with basically something that's very similar to serial. So what this flow allows you to do is to take a module like this that's implemented in a completely different way and replace this with a Verilog implementation of the same thing. So let me just demonstrate what this does. If we go into the terminal, what we can do is telnet into it, and we can type, and what it'll do is it will respond with a copy of what we just wrote. So internally what it's doing is, if we just make this a bit smaller so you can kind of see. So what it's doing is it's reading the data as it comes in off of the UART, and then it's going into the first FIFO. A FIFO is just, you can think of it like a queue. It's just a line that the data sits in until it's ready. So, or you can also think of it kind of like a buffer. It's a first in, first out buffer, essentially. So it reads it off the UART, it goes into the FIFO. Then once you press enter, there's a circuit down below. Let me just move this up a little bit. There's a circuit down below, the finite state machine, and it's looking for the enter key being pressed. And when the enter key is pressed, it triggers the receive FIFO to drain into the transmit FIFO. So it just copies all of the data over to the transmit FIFO. And then once that's done, it triggers the transmit FIFO to start sending that back to the UART. So what the UART ends up doing then is just echoing back what you just said. So there we go. So where do we start trying to convert this design into something that we can run on an FPGA? Well, the first thing that we can't do is output this UART, because the UART can't be synthesized because there's no telnet on an FPGA. So let's go into here, and we're going to go into circuit specific settings, and then we're going to go into the advanced panel, and we're going to go down here to skip in Verilog VHDL export. So we want to check that, and then we need to go into other things in the circuit that we can't send out to Verilog. So let's save that. And then in the FIFOs, we also have block RAM. And the interesting thing about digital is in digital, there's no synchronous RAM that acts like block RAM in the FPGA. There is a block RAM component, if I can find it here, block RAM. There's a block RAM component, but it's not dual port. There's separate data in and data out ports, but there isn't two address ports, if that makes sense. So this doesn't quite work the same way as block RAM in the FPGA does, and so we can't really use it. But if we take regular dual port RAM and we put a register on the output, Or we could put the register on both of the address ports. That would be more accurate to what happens in the FPGA. But it's 2 registers versus 1 register, and it does the same thing. So we put the register on the output, and then it will act just like the block RAM in the FPGA acts, because block RAM is synchronous, which means there's a register on the address. So it won't read or write until the clock pulse goes high, which is a pretty big gotcha if you design your circuit around what you can do with asynchronous RAM. But one trick is you might be able to negate the clock. And if you can do that, then that may allow you to get away with not having to wait until the next cycle, because you can just wait halfway through the cycle to get the result that you want to read. But if you can't do that, yeah, there's ways of modifying your design so that you can accept that the data won't arrive until the next clock cycle. So this obviously is not synthesizable on the FPGA because the block RAM on the FPGA has this register built in. Now, if Yosis was a little bit smarter, it could detect, hey, there's a register after it. This is the same as block RAM, but currently it doesn't have that ability. I don't know, maybe by the time you're watching this, that will be fixed and it'll be able to infer the RAM properly, but currently that's not the case. So what we need to do with this circuit as well is we need to skip in Verilog VHDL export. And both of these FIFOs are the same, and so both of them contain that block RAM. So we only need to do that once. So at this point, all that's left is the PLL, and we also have to mark the PLL as skip in Verilog VHDL export, which it looks like I already did. And this is all I'm doing with the PLL is I'm just sending the input clock right to the output clock, and then there's a reset object that will basically send a reset pulse at the beginning of the circuit simulation. And I'm just using that for the locked. Locked just means that the PLL has locked on. So it takes a while when the FPGA first resets or powers on for the PLL to lock on to the input frequency and stabilize at the output frequency. So that's what this signal is. And you can use that to feed your reset network. So in this case, I'm just putting it through a NOT gate to invert it, and then that's used as the reset for the rest of the circuit. Other things that you might want to check to see, some things are not synthesizable, so you might get errors when you go to export it to Verilog. So if that's the case, then you might need to fix that, or you might need to put it into a circuit that you can remove using the technique that I just said. Trying to think if there's anything else. I don't think so. Let's move on. So once you've got all of those set up, you've got all of your block RAM replaced. Oh, and by the way, I just remembered one more thing. ROM can also be synthesized, but not this way. You have to put a register after it, and then you can use block RAM as a ROM. So that's one way of having a very efficient ROM if you have spare block RAMs. But like I said, all of the memory in the FPGA is synchronous, so you have to put a register after it for it to behave the same way as it does in the FPGA. And if you are using the Icebreaker or the Ice Sugar or anything else with an UP5K FPGA, there's also built-in RAM, which actually this block RAM will work just fine for. So you can use this block RAM for the single port. It's called SP RAM in the documentation for the UP5K. So you can use the block RAM for that. And actually this might export properly because I believe this is synchronous. So you can try it and see if it'll work properly. Oh wait, no, you still need to put it into a subcircuit and mark it as you can't export it because there's some special syntax that you have to use in order to utilize the single port RAM because Yosis doesn't infer it yet. Inferring is the process of taking some Verilog and mapping it to the hardware. And currently it's not smart enough to map the SP RAM. So you need to, yeah, you need to mark it as not to export. So let's save this and let's export it. So export to Verilog. So what I'm going to do is I'm going to create a new folder and I'm going to call it RTL. RTL is Registered Transfer Language, and it's kind of a blanket term for Verilog and VHDL. But you could call this HDL for hardware definition language, or you could just name it Verilog for your Verilog code, or whatever you want to call it. I'm just going to call it RTL, and I'm going to save the Verilog here. Now, when you hit save, it may give you a very cryptic error and vaguely point to something that it can't export to Verilog. It takes some trial and error to figure out exactly what it's talking about, but hopefully you can figure it out and fix it. Like I said, it's often just moving it into a subcircuit and then marking that subcircuit as don't export, and that usually fixes it. So let's move into Visual Studio Code. So here's our Verilog. Digital produces very readable Verilog. I'm actually quite impressed by how readable this Verilog is. So if you want to learn Verilog, try building stuff in digital and exporting it to Verilog and seeing how that works, because it's very illuminating. Okay, so this is the primary module, and you can always find it right at the bottom. So you just go to the bottom and work your way up until you find module. So these are the inputs and outputs that we'll need in order to run this. So what do we do first? Well, first things first, let's create a makefile. Now, if you're on Windows, you might have to call this .mac or something like that, or .mk, just because Windows prefers to have a file extension. It doesn't like files without one. But since I'm on Linux, I'm going to name it the standard way I would on Linux. So we've got a makefile. What do we put in it? Well, one of the first things I want to do is I want to get this working with Verilator. So, well, actually, I guess there's one thing that I need to do before that. I need to set up a replacement for each of the modules. So if you look in the Verilog, you'll see that the PLL is referenced here, but if you search for that, you won't find it anywhere in here, which means we need to supply a replacement version for it. So what I'm going to do for the PLL specifically is I'm going to copy in this. And what this is going to do is run IcePLL in order to generate a PLL.v. So if you go on the command line, you can see cd RTL. So let's just make this a little bigger. So what IcePLL is a program for generating the PLL configuration. So it'll take an input frequency, and for both the ice sugar and the ice breaker, I believe that input frequency is 12 megahertz. Although the ice sugar, it might be configurable, because I believe it's generated by the microcontroller on board. There's a little ARM microcontroller there, and you can configure different output frequencies, I think. But I'm just going to presume you have it in the default configuration of 12 megahertz. Then you would set up an output frequency, and there's a few other options in here. Namely, you probably want to write it to a file, and you want to generate a module. So those are the things that you'll need. You can also change the name, but I'm just going to use the default name. And yeah, that's basically it. So if I go make PLL.v, did I not save it? I did not. What I'm doing is there's a couple of things that I needed to change in the default output, and there's no configuration settings for it. So I just use sed to do basically a regex search and replace. So I'm just replacing PLL core with PLL pad, because you need to take the clock from a pad. And so there's a different primitive to use for that. The primitive being this special module name. And there's a bunch of built-in special module names that are called primitives for the built-in hardware on the FPGA. And then one of the differences for the pad version rather than the core version is the input clock is not called reference clock, it's called package pin instead. So I just replaced both of those in the generated file. So if we look at the generated file, you'll see it has the input frequency, and it tells you what the requested output frequency was, and it'll tell you what it was able to do. So the PLL only has certain frequencies that it's able to do, and so it'll just round it to the closest one of those frequencies. And in this case, it'll be good enough. And then essentially what it's doing is it's just configuring this primitive here to have these certain parameters. And that's basically it. It calculates these parameters for you, which is nice. So essentially then that's done because I made sure that the pins in digital were named the same things as these pins. So if you look in here and you look, they're clock in, clock out, and locked, which is the same as in the PLL file. So that's one file down. We've got the UART to replace, and what I'm going to do is take some open source code that I found on the internet and had to only slightly modify. So I'm going to create a new folder. Now, the reason why I'm doing a UART is that one of the first things that you'll want to do with your design is be able to talk to it, and having a UART set up so that you can talk to it from a computer is really, really handy. So, and believe it or not, I don't have this set up for my CPU yet. So I don't actually have a way to talk to it. And so this tutorial is my way of getting that all set up. So one of the things that will be required is setting up the UART baud rate. So the way that's going to work is there'll be an enable signal that happens on a periodic basis. And that's what this code is going to do. And by the way, this is from the icebreaker examples. So I just took the icebreaker example code. Looks like it's MIT licensed or BSD, I'm not sure. And yeah, there's all of the fancy formulas and stuff here for figuring out how to have a signal that pulses at the baud rate, essentially, given the input clock. So that's what this module is doing. So we've got this one, and then we've got a UART receive module, and that one has this code. So this is basically just a state machine for receiving data at a certain clock frequency or a certain baud rate. And it's got all of the code in here. I don't fully understand how this code works because, like I said, I barely understand Verilog. So that's that one. Then, of course, if we're receiving, we need to transmit. So here's the transmission code, and it's comes from the same place, icebreaker examples, and it's basically the other way around. And both of these use the baud tick gen that we just entered in. And then, of course, we've got the UART itself. And this one I mostly wrote. I still gave credit to the author because I took some of it. But one thing to keep in mind is that you need to set this clock frequency here to be the same as what the PLL is going to output. So the PLL is going to output 29.625. So this needs to be the same. And of course, our baud rate is going to be that. So this basically combines the transmit and receive code. And digital doesn't really support parameters, so I can't just pass in the clock rate from somewhere else. Although I suppose I could make it a define so that it's the same in all places. But anyway, yeah, so there's our UART. So that's that piece of the puzzle. And I've made sure that the pins are the same. And what else? We've got the block RAM to replace. So we need block RAM. And this is the magic formula for block RAM. And I just found this by searching online to try and find out what the standard way of doing block RAM is. There's a blog article, zipcpu.com, I think, and they had basically a tutorial on how to make a module that will be inferred properly by Yosis. And there's two rules to keep in mind. There's an always block, and it can only have a single if statement if it needs an if statement. And you should separate the always block for the read side from the one on the write side, because the inference code in Yosis is pretty rudimentary. So sometimes it has trouble figuring out that you want a block RAM, but inference is usually the best way to do this because the built-in primitives are pretty tricky to use, and inference basically smooths that over. So what this is doing is it's setting up a memory. This is the block RAM itself as an array of registers. And then on the positive going edge of the clock, it reads that memory and writes that memory. And this could be pos edge or neg edge because the block RAM supports either clock polarity. So if you need to go on the negative edge, that's how you would do it here. Not sure what else to say about this. It's pretty straightforward. It's just reading the memory into an output register, and it's writing the memory to the memory array. And it does that at the clock edge. So that's everything here. By the way, if you wanted to make this into a ROM, you would do an initial block. And there's mem hex, no, read mem h or something like that, I think. Yeah, and then you specify a file name, test.hex, and the mem. I think that's how you do it. Something along those lines. You can look it up. If you just Google Yosis block RAM ROM or something like that, and it'll give you the magic formula for doing a ROM. Likewise, if you were doing SPRAM, you'd have to use the actual SPRAM primitive, and I'm sure you can find that by Googling around as well. So we've got block RAM, we've got a UART, and we've got the PLL. So it seems like we should be able to get Verilator running, right? So let's try that. Here, let's get the linter running first. So what I'm doing is I have Verilator and I'm running it in lint only, so it's not going to build anything. I have all of the warnings turned on, and then I need to turn some of the warnings off because the code for, and actually I'm going to move this down here. The code that digital produces a few warnings, so I just turn those warnings off. Specifically, it's not careful about the width on certain operations. This warning is pretty useless. It's just saying that your module should have the same name as the file name that it appears in, which makes no sense. And then this no pin missing, digital just omit the pin if it doesn't need it. So who cares? That's fine. The other thing that we'll need is we've got this add source variable that we're using here. So we need to define that. So here's a variable for that. And we're just listing all of the UART code as well as the block RAM there. And one thing that I'm going to do is specify this sim PLL. And the sim PLL just simply sets up a version of the PLL code that Verilator will like, because Verilator doesn't know about the built-in PLL. There are ways of getting Verilator to know about it so that it'll compile properly, but I'm not too sure how to do that myself, so I'm not going to cover that in this tutorial. I'm just going to cheat. So PLL sim is the simulation version of the PLL, and it's essentially doing exactly the same thing as the module in digital is doing. It's just sending the clock in to the clock out, and it's also just sending the locked input as 1. So it's always locked. So then we have that. So we should be able to lint this now. Let's do that. Make lint. And it passed. No problems. Okay. Surprise, surprise. I got this all working. So when the first time I ran the linter, I had to fix a bunch of issues. And don't be surprised if that's the case for you as well. So, and again, if I haven't mentioned this before, all of this code that I'm copying and pasting into here is up on my GitHub. It's in the tutorials folder. I will put a link in the description for it. So don't worry too much about trying to copy this off of the video. Probably should have said that earlier in the video if I didn't. So yeah, this is a magic thing. You can just copy and paste it from the tutorial folder on my GitHub. All of this code is MIT licensed. Don't worry about stealing it, changing it, using it for profit. I don't care. Just use it. It's available. It's right there. So all of the code in this tutorial I've made sure is either MIT or BSD licensed. So use it commercially if you want. It's no problem. So where was I? Oh yes. So we've got the linter working. Now we need to get Verilator working. So the next thing is to get Verilator working. This is going to be a two-step process. The first step is to actually compile it. So, oh yes. And of course, we're going to need some C++ code. So what this code is doing is it's just running Verilator, and it's doing the same thing where it's ignoring certain warnings. And there's this trace variable, which I will define. Let's put that up by the ignore warnings. So this trace variable basically tells it to emit a fast file, and that fast file can be used in GTKWave to inspect what's happening inside of the circuit while it's running. Well, not while it's running, after it's ran, but that's very helpful. So all you would have to do is uncomment this line and it'll run it with tracing enabled, but tracing enabled will slow it down a bit. So that's why I don't have it always on. I just turn it on when I need it. And then there's a bit of make file magic. This is just changing the file extension to .v, I guess. And then there's adding the source and the sim PLL, and it's producing an exe, and it's taking the main.cpp. So we need the main.cpp, and we need the telnet UART, which is the C++ version of the UART code that basically talks to the UART. So main.cpp, here we go. So here is the C++ file for Verilator. And all this is doing is bootstrapping and running the design. So I have this special stuff here that's just making sure that if trace mode is activated, then it'll load the trace module and start running that. And I have that here as well to make the variable that's required. Here it's parsing the command line arguments, and here it is creating a new Verilog module. So what it'll do is it'll compile the Verilog into C++, and then that's what is being instantiated here. And then I have a telnet UART module that I wrote because I couldn't find one that was MIT licensed. So now there is one that is MIT licensed. So this will talk to the UART in the Verilog itself. So, and then of course here is opening the run.fast file in case it needs to, only if tracing is enabled. Then here it's just initializing the circuit. And then there's a main loop. And in this loop, all it's doing is toggling the clock off and then toggling the clock on and simulating the circuit itself. So what the telnet is doing is it's activating the TX and RX pins to talk to the Verilog circuit itself. And then I basically just close and clean up. And this loop will continue to happen while done is true. And this telnet step function returns whether it's done or not. So then we need the telnet UART code. So I have written up the UART code, and this is kind of scary, just warning you. But feel free to grab this code and just use it. You might need to tweak it a little bit for your circuit, but I've tried to make it relatively commented and easy to read, hopefully. So what it's going to do is it's going to open a telnet connection, so it needs the socket libraries. I've written this in kind of a hybrid C style because I'm not a C++ programmer. I don't know C++ very well. I know enough to be very dangerous, and that's about it. So I prefer just writing it C style. But this is kind of not even C style. It's kind of like a mutt between C++ and C. So if this drives you bananas, I apologize in advance. Anyway, enough disclaimers. This is not the best code in the universe. It's fine. And actually, I should probably put the, where is it? I'm just going to put the copyright up here. There we go. There we go. Yes. So this number here needs to be the same as the number in the UART.v. So these numbers have to match. Then there's a couple of state machines that get built, and those are controlled by these structures. And again, if I was more confident with classes, I would build classes, but I'm not. So you're getting structs. This is the init code, and all it does is open a server socket and then waits for a connection. So all you have to do to connect to it is follow the message that it prints, and it'll tell you what command to run, which we'll see in a moment. And then, yeah, it just sets the RX pin 1 to 1 because that's what's expected. And in order to use this code, you're probably going to need to change a few things like the types of the top file, for example, and probably a few other things. And yeah, here's the cleanup code. And then here's the state machine for each of the sides of the transaction. And the state machine is pretty straightforward. There's an idle state that it's in most of the time until, well, for transmitting until it receives a byte from the socket, which the socket is the telnet connection to the program. And then it checks if the byte is one of these, which could indicate that a control D or control C was sent over the connection, and that's the way to gracefully exit the program. Otherwise, it prints it out to the screen, so it's doing an echo, well, local echo. It doesn't do a remote echo, I don't think. No, I think I removed that. And then, yeah, it's doing a non-blocking read. So if this was running on Windows, I don't think Windows or WinSock supports just having receives that are non-blocking. I think you need to do this a different way. I don't know enough about Windows to be able to do that, but hopefully Windows subsystem for Linux will just do the right thing. And then it goes into the start state, which is sending the start bit, and then it sends out each individual bit after that, and it waits the certain number of ticks for the baud tick. So it's basically doing the opposite of the Verilog. And then once it's done, it goes into the stop state and it sends the stop bit and then goes back to idle. And the same with the RX side, except that it's doing it for the receiving from the Verilog itself. So it has RX idle and it waits until the TX line goes high. And then when the TX line goes high, that means, or low rather, it waits until it goes low. And when it goes low, it knows, oh, okay, the circuit wants to transmit to us and we'll receive it. So then it waits for 1.5 baud ticks so that it can sample it right in the middle of the bit. And it just skips the start bit because the start bit's always 0. And then it goes into the receive code. So it's just shifting it into the receive buffer. And then once it's fully received, then it prints it out to the to standard out and sends it to the other side of the telnet connection. And then it waits for the stop bit before it resets its internal state. And then we basically have both of those steps being handled in the same function. So that's basically that. So I think we have enough now that we can actually run Verilator. Let's save everything. Let's close all to the right. All right, let's set up the build step, or the run step rather, because we can build it, but we need to also run it. So I'm going to make a rule called sim that will run the binary that gets produced by Verilator here. And I'm going to move this down because that's where it was. So yeah, it's just CDing into the obster, which is what Verilator produces by default. And it just runs the binary that gets built by make here. So let's run this. Did I not save? I did not. All right, it's building and it tells us that we've got a telnet port to connect to. All right, let's do that. Test. Aha! And you'll notice that it's much faster than digital, although I had the clock rate set pretty low in digital, but Verilator is a few times faster than digital is for the same size of design. So that's a useful thing if you want to be able to simulate your circuit a little bit faster. But the main thing is you can turn on tracing. So let's do that. To get out of here, I've just made it so that you can just go Control C, or you can do Control D or whatever, and it should exit. Control something is very likely to exit. Okay, so we've got that. Let's turn on tracing and I can show you why you would want to use Verilator, because this is the primary reason. So we've got trace here. Let's uncomment that and let's build it again. So we got to go, well, the easiest way to reset it is just to do RM RF obster, and then we remake it and we connect to it again. All right, so, and then we exit out, and then we go GTKWave obster run.fast. And here we go. We've got GTKWave, and I'll just make it a little bit bigger here. Pardon me if this is a little bit small to see on your mobile phone. I don't know if I can scale the interface on this. So here we go. We've got the clock. So that's our clock. We also have the RX line and the TX line. And what's really awesome is you have access to the entire circuit. So we could go into the UART and we could go into the tick gen and we can put in our tick signal. So that's the RX tick signal, and we could put in the TX tick signal. Those should be the same, I would think. Oh, they're not. Interesting. Huh. So then we've got those tick signals and we've got RX and TX. So let's just do a little bit of zooming out. So here's our tick, and do we have any data? Here's our transmit signal. Yeah, so you can see that it transitions on the tick signal. And again, if you're looking at this on mobile, it's probably really, really small. I apologize. You can see every single wire in your entire design. So I could inspect, for example, the RS flip-flop inside this thing, and I can see what the outputs of the RS flip-flop are. And I can see that the flip-flop triggered there and there. So it just gives you a lot of insight into exactly what's happening in your design, and that allows you to debug a lot of things, especially timing problems. So yeah, it just makes a huge world of difference to be able to go into your design and see some waveforms that tell you exactly what's happening at any given time. And you can set these up with different colors. So I could change this one to yellow, for example, and you can change a bunch of different parameters in here to make it a lot easier to like study it for any given length of time. But anyway, I've found this tool absolutely invaluable. So let's move right along. We want to build this on the FPGA. So let's do that. So we've verified that this actually works in Verilator, and I've had to tinker quite a lot on this particular circuit in Verilator to get it all working so that I had some confidence that it would work on the FPGA. So the final step is to synthesize this on the FPGA. So let's just copy and paste a bit of code in here. So what this is doing is it is doing some magic make stuff to convert a Verilog file into a JSON file. And it's also taking the extra source, and it's taking a FPGA version of the PLL, which I'm just going to create a variable for up here. So that's the FPGA version of the PLL, and it's running Yosys on it. It's telling Yosys to produce a log file, and it's running this command in Yosys, which is synth ICE40, which means synthesize for an ICE40 FPGA. This means the top module, so it's trying to figure out what the name of the top module is, which it's doing by taking the output and removing the .json on it, so it's just the plain word. Then it's saying to produce a JSON file at the end, which is the same as the output file, which is, in this case, FPGA 101.json. And it's taking the input file as well as some additional Verilog files. So the additional ones are the add source variable and the FPGA PLL variable. And so that will produce a JSON file. And then with that JSON file, it wants to convert it into an ASC file. And the ASC file comes from NextPNR. And this one also is going to produce a log file. Since both of these programs produce a very large amount of logging output, and you'll probably want to search that output for various key things. So then that just makes that easier if it's just in a file. And then I have NextPNR ops, which I need to create the variable for. I'm also going to comment this out. So some of the options that you'll want is to allow the PCF file to have unconstrained pins, which is fine. You don't necessarily have to have them all constrained. And I want to optimize for timing. So I want it to try and reduce my clock rate as much as possible if it can. So it'll try and make a bit better decisions. It's not as good as the commercial tools. It is open source after all, but it's a lot faster than the commercial tools. So yeah. So then we've got an FPGA type and an FPGA package. So we need to specify those. So we have an up 5K FPGA, and you change this to ICE40 if you had an ICE40 FPGA. And then you also have to specify what package. And in this case, it's an SG48. And you'll find this code in the datasheet. So these are the magic things for ice sugar and an icebreaker. If you have a different FPGA, you'll have to figure out what these parameters are. And then you also need a PCF file. And I happen to have a PCF file for ice sugar. And PCF is a pin configuration file. And I just have a bog standard PCF file that defines all of the pins. What you're supposed to do is only have the pins defined for the pins that you actually use in your design, but I find it more helpful to have a standard PCF file that just defines all of the pins. So all of the PMODs are in here, the clock is defined up here, and all of the switches and the LEDs and also the USB port and the flash, all defined on here. So then you can just grab this PCF file and use it. I also have a PCF file for the icebreaker, and this will be, both of these files will be available on my GitHub. So there's the PCF file for the icebreaker, and I've made it so that these files are basically interchangeable. They all have the same names, I believe. Might be slightly different names. Yeah. Okay. Yeah. And there's a button that's available that isn't available on the iSugar. But anyway, mostly the same. For this design, the pin names should be the same. So all you'd have to do in here is change the PCF file from, I'll just put them both on here. So all you'd have to do is comment this out and uncomment this one, and you've got the icebreaker. So I'll leave the ice sugar because that's what I have. I don't have an icebreaker, but I'm pretty sure all of this should work on the icebreaker as well, since they're very, very similar. I'm just trying to see if there's anything I've missed. I don't think so. So So that's Yosys, that's next PNR. I believe we've got everything for next PNR, and then it produces an ASC file, and then I have the ASC file going through IceTime, and IceTime produces a very similar report for the critical path as next PNR does, but it produces it in a slightly different format, and so the one that IceTime produces can sometimes be easier to read. So I just have it producing both. So I'll have a critical path report from next PNR, and I'll also have one from IceTime, and that can sometimes help me figure out where the issue is. So critical paths in a FPGA are the path through the circuit that is the one that is causing your clock rate to be the maximum that it is, if that makes sense. So if you can reduce the critical path by making it faster, then you can increase the clock rate that you can run inside the FPGA. So that's why you would want to have the timing report. And then, of course, we're using IcePack to produce a bin file. So let's run this. Make FPGA 101.bin. And there we go. It ran. And let me just talk while doing this again so that, well, I have to clean so that you can see that it is incredibly fast. Let's do a rule for cleaning, and this will just clean up all of the temporary files. So then we can run from scratch. Make clean. So I'm going to talk through this so that my auto editing script doesn't speed it up. So you can see here that this is running very, very fast. It took 2 seconds, something like that. Commercial software is a lot slower than this from what I hear. So yes, it's quite nice. Now, the last thing that is missing, because we have a bin file now, we just need to actually upload this to the FPGA. So let's do that. Upload. So I'm going to use Ice's prog, and I don't have to because the Ice Sugar has a built-in way to do this. So I could just drag this bin file onto the drive that appears when I plug the Ice Sugar in, but I'm going to use Ice's prog, and you use Ice's prog like this. And if this was the Ice breaker, then just remove the S in the middle, and it's Ice prog instead of Ice's prog, and that will write to the Ice breaker. So yeah, let's write it. Make upload, and it's writing, and it's done. All right, let's connect to this thing because it's running now on the FPGA. Sorry, I don't have a webcam showing the FPGA, but I don't have that set up, so sorry. Just need to find the command here to run. So I'm going to use a program called PicoCom, and if you don't have PicoCom installed, you can install it using your package manager of choice. I'm using PicoCom because it's configurable, and I need these special settings to act like a telnet terminal, because a telnet terminal and a serial terminal have different behavior, and I'm trying to smooth that over with these extra parameters. It's kind of cheating, but I didn't want to have to make the circuit more intelligent than it currently already is to deal with the differences between the two. So there's a bunch of garbage on the screen that you can just ignore, and we can go test, test, test. This is a test. This is working on the FPGA. So the FPGA has exactly the same behavior. And part of that is because we went from digital to Verilator. We got it working in Verilator. And then on the FPGA, the only weird thing that I had to deal with was the difference between a serial terminal and a telnet terminal. And that was mostly just tweaking with PicoCom until I got it to behave the same way. And I had to do a few fixes to the circuit itself. But it's now running on the FPGA. So we've got this circuit here. And actually, one of the fixes that I needed to do was I needed to add this circuit here that just converts 0 into a new line character, because in telnet, the new line is sent as a null byte, which is 0. But in the serial terminal, it's sent as LF. Just not quite 100% accurate, but mostly, yeah. And this kind of just smooths over that difference. So we have a design that works in digital and uses a UART, which I think you might find is quite handy, since the very first thing you got to do when you have an FPGA design is you need to be able to talk to it somehow. And a UART is probably, it's not the easiest, hence why this tutorial covers setting up a UART and getting that working, because that's probably one of the first things that you'll want to do, and it's not straightforward to do, unfortunately. But like I said, all of the code that I just showed you is MIT or BSD licensed, so go take it and get it working. So yeah, I hope this has been helpful, and if you have any difficulties or troubles, feel free to leave a comment on this video, and me or somebody else that is looking through the comments will answer. If you really have some trouble and it's a bit more explanation than a YouTube comment will allow, feel free to open an issue on my GitHub, and I can see what I can do to help out. So thank you very much for watching. I hope you have a very great day. Bye.